Today we continue with our discussion on error control codes. The discussion will be intuitive except a small example of a very famous code known as Hamming code later on. As you may remember, we were classifying the error control codes, like some codes or many important and popular codes are classified as block codes. Then there is another class of error control codes known as tree codes in general, and convolutional codes form a very important family of that. And then we went for further classification, and in the process we also had a brief idea about block code structure, why they are called block code, and convolutional code also. Then towards the end we classified the block codes a little bit further. We said that the block codes may be non-binary in nature or binary in nature, and then the block codes may be systematic and non-systematic. Similarly, the binary codes may be systematic and non-systematic. To give you some examples, with some names of the codes, so that I remember the names at least, if not the finer details, let me tell you that under the category of block binary codes, there are several codes available. To start with, the example that we will consider later, Hamming, named after R.W. Hamming, who first proposed this coding scheme. Well, Hamming code may be both systematic as well as non-systematic. In fact, the original code that he had suggested was non-systematic in nature, but with subsequent development of theory, it was found that we can give a general nature to Hamming code. In fact, nowadays all binary codes which correct one error in one block of n bits, okay, is in general called as Hamming code, and the code may be systematic, it may be non-systematic. That is why I am giving the example here. So, it may be systematic, may be non-systematic. Original code due to Hamming was non-systematic, but there is an equivalent systematic version also. In fact, we will see somewhat later that for a block binary code, it is, and a cyclic code specially, it is possible to put a non-systematic code in a systematic way and vice versa without sacrificing any error correction capability, etc. Then the another example, a very famous example, is known by this term BCH. BCH, it represents the name of three pioneering researchers really in this area of error control coding: Bose, Choudhury, R.C. Bose, D.K. Choudhury, and Hockenheim. I am not writing the full form for you, BCH will be sufficient. Then there is another famous code which was extensively used sometime earlier, even now this is popular, is known as Gole code, again named after the inventor, is a Gole code. So, these are three examples of binary block error control codes. Then in the non-binary category, some of the BCH codes can be non-binary, and a special form of that which is known as RS code, Reed-Solomon code, named after I.S. Reed and G. Solomon. RS code is a famous example of a non-binary block code. It can be systematic as well as non-systematic. And in between, I could have put another classification calling codes, block codes, as cyclic or non-cyclic. I have not done that to save space and time here really. Most of the popular error control codes in the block category, they are cyclic in nature as well, which simply means that if you have a code word, then if you give a cyclic shift to the code word, whether it is binary or non-binary, you get another valid code word. Okay. Under the tree category, tree codes, again as I said last time, it may be binary and non-binary. However, most of the popular codes are binary in nature, and the code may be systematic or non-systematic. Let me indicate the systematic and non-systematic portion only. Sir, yes. Sir, what exactly do you mean by cyclic shift? are familiar with left shift, right shift operation. So, if you imagine that a code word is stored in a buffer shift register, then if you give an end around shift, cyclic shift, that means the last bit becomes the first bit with one shift really. The first bit goes to the second place and like that. Then again you get a bit pattern with the same length as that of the code word, say n bits. Now that also is another valid code word corresponding to a different message pattern.
But while shifting, shift cyclic shift, you perform additional operation.
No additional operation. You can perform really in general. No, not that really. See, in the very general definition of a cyclic code is that uh, not only end around shifting really, you can add another valid code word to that, and even then if you give a shift really, you get another valid code word and properties like that. Okay, but no further operations like encoding etc. Or arbitrary XOR operation of any 2 bits in between, those are not to be done. Then the property is destroyed.
But those are parts of error control coding, aren't they? Like cyclic redundancy check, or if we are appending some other parts to the block.
Right. What you are talking about is a kind of code which is now known as CRC, cyclic redundancy check. Okay, that's an error detection kind of code only. Okay, which means that you can detect the presence of errors, large section of errors, large kinds of errors there by simple checking mechanism. Okay, the target there is not full correction as well really. So those cyclic redundancy check codes, they usually belong to this category. They are block binary codes. Okay, but you do not correct errors there because error correction needs further operations and somewhat more complexity. Okay, you do not need it in local area network environment where two computers are very securely connected with a cable. Okay, and if there is any error, you can easily request a retransmission from the other computer really, and it can retransmit. So depending on the application, once again I say really you have to decide what kind of code is to be used and for whether only for detection or for detection as well as correction. Okay, under the tree code, as I said, there may be systematic codes as well. Now, last time we were talking about some Viterbi algorithm. Okay, there are many popular non-systematic binary convolutional codes, okay, which have been used extensively, which are still in use in many wireless communication systems like satellite communication systems, like mobile systems, where non-systematic binary convolutional codes have been used. Okay, of late there has been, in fact initially it was thought that systematic convolutional codes are not many in number and they do not have very good or best error correction capability. Of late, with some remarkable development in the area of error control coding, specifically on turbo coding and decoding, the systematic convolutional codes have become popular once again. Okay, now they are also very popular, and there is a sort of tussle really when it comes to formulating a new standard. In some cases, you will find the turbo codes, which essentially uses more than one systematic convolutional codes, are favored. Though there are situations still where this classical, more classical non-systematic binary convolutional codes are also preferred. Okay. So, as an example, under systematic convolutional code, let me write turbo code. We will not discuss about this. Now, we try to understand the basic issue of decoding, and from this point onwards we will assume for easier understanding the binary block code. Okay, so I say a heuristic decoding algorithm. What the issue is, okay, when we are considering a binary block code. We remember that a binary block code means there will be a block of n bits which will form a code word. Okay, out of these n bits, k bits will form the message bits, and the remaining n minus k bits we have called as parity bits. Fine. Now, please note that like the source we talked about earlier, this group of k message bits per block, okay, k message bits per block, this group of k message bits, they this combination of k message bits may be anything. In fact, this error control coder decoder designer or the communication system designer should have no say on which particular pattern of k bits will come next, is it not? So, in short, I can say this group of k message bits is unconstrained, that depends on the source property really. Okay. So, then can you tell me how many possibilities, how many different message groups of k bits each are possible? 2 to the power k, 2 to the power k, no minus. I have got a k bit combination, okay, k bit group, okay, and the pattern may be anything. So, the maximum number of patterns is 2 to the power k, okay, 2 to the power k message groups, let me write, are possible. Okay. Now, let me consider a particular group of k message bits as a point in an n dimensional space. Can I do that? And a k bit message pattern, okay, let me consider this k bit message pattern, a specific one, as a point in a k dimensional, not n dimensional, k dimensional space. Can I do that? Okay. Each message pattern can be mapped into one point in a, I am writing k dimensional for the time being, in a k dimensional space. Can I say message space? Okay. In general we say signal space, but here I can say k dimensional message space. Is that agreed? Fine. If k is 3, as if I am considering a 3 dimensional space, a 3 bit combination is 1 point and there will be 8 possible combinations. Okay. So, there will be 8 points in that space, message space. So, I am extending the idea to k dimensional space. Now, tell me quickly, is there any point vacant in this message space? Then I say that the message pattern, bit pattern of length k can be of anything, can be of any pattern, any possible pattern is accepted. Then will there be any point in this k dimensional message space which cannot be occupied by the message pattern? Okay, because a k dimensional message space will exactly have 2 to the power k message k points really, and because the message is unconstrained, so all the message groups or patterns will have 1 point each in the space. So, I can say that this space is filled up totally. Okay. A filled space. Yes, please.
So three dimensional, suppose K is three, then three dimensional message space.
Yes.
So because we are considering only binary combination, is actually a rectangular parallelepiped with 8 vertices, right? Any point within that, sir, is empty, sir.
You can't define that point perhaps using 3 bit binary representation. The length increases, isn't it? So, in that case you are essentially not talking about a 3 dimensional space really. The dimension has to increase. Okay. Is that okay? So, this message space is filled up So message pattern may be anything. So there is no redundant signal point, redundant point in this space. Okay, but that is the reason why in the block coding and in convolutional coding also indirectly we have to bring in some additional bit patterns, which we said for the block code. Again, for the example that I am assuming that we will have some additional parity bits, which means that we are trying to stretch, we are trying to create another space, maybe code word space, okay, whose dimension invariably is greater than the dimension of this message space. So what we have done in our earlier example of the block code, we considered a group of k bits, we added n minus k bits, so that we got an n bit code word. Okay. So then how many points are there? If I now consider an n dimensional space, n dimensional, let me write code word space, because we know what the code word is. Code word is the whole block of n bits that we got after adding those parity bits. So how many points are there in this n dimensional code word space? Again 2 to the power n. So 2 to the power n points. Now we have in that n dimensional code space. Is it greater than 2 to the power k? It has to be. It has to be. Okay. So it is greater than 2 to the power k. In fact, in some, depending on the values of n and k, okay, we can even say that this is much greater than 2 to the power k. Though it need not be always. If k and n are very close, then it may be 2 to the power n may be just greater than 2 to the power k. Fine. How is this situation? Let me try to depict. I can't draw an n dimensional space here really. Okay. Let me arbitrarily give an idea that, okay, suppose this is my n dimensional code space, fine, and there are 2 to the power n points. Now, can you guess something about the coding strategy or encoding strategy? How should there be some plan while we add this n minus k bits to a group of k message bits? The idea is to see there is a one-to-one mapping of each of these k bit message pattern to one point in the n dimensional or higher dimensional space, code word space. Is it not? So let us remember that there is a one-to-one mapping. Would you like this one-to-one mapping of a k bit message to an n bit code word? Would you like to have this one-to-one mapping, that a particular pattern of k message bit should result in a specific group of n message bits, n code words? Why? Why? Otherwise, there will be problem really. You will the decoding will not be unambiguous sort of thing. So this one-to-one mapping should be there. That means in this n dimensional code word space, I have 2 to the power n points, but for this encoding operation, I do not need all the points really. How many points do I need in this code space? Only 2 to the power k. So then I can say that the issue of encoding is nothing but placing only 2 to the power k points in a very judicious manner, maybe in the best possible manner, into this higher dimensional space which has got many more number of points. Yes.
If there is any relationship between the next coming data and the previous coming data?
For block code, we have cautiously excluded that. When we are for a block code, we accept a block or group of k bits we encode it, okay, and we leave no trace, so that whenever the next block of k bits, the k message bits comes, we encode them in an identical manner, okay, without any effect of the previous blocks of k bits. Okay. So, encoding then in general I can say is an intelligent way of mapping 2 to the power k message patterns, possible message patterns in an higher dimensional signal space, such that what would you like to maintain some condition really. For example, would you like to, just going by this diagram, would you like to choose as one code word and this as another code word point?
There will be two nearby.
Oh yeah, that's the point, isn't it? You don't like that. You do not like that.
Because error in one code word will result in nearby code word.
Exactly. That's the reason, isn't it? See, the impression that I was trying to create here is that between these 2 points, as if the distance, whatever way it is defined, the distance is less compared to the distance between this point and say this point. Okay, which means we have to talk about some kind of distance measure. Okay, and then that may be very useful in choosing 2 to the power k points from this 2 to the power n points. Okay, and that's how he said that, well, apparently these 2 points are very close. So, if I talk about some kind of distance really, maybe the difference between these two, or the distance difference is very small, or the distance is very small. Okay. One very popular measure of distance, especially for these binary codes, is, that is also named very rightly after Hamming, is known as Hamming distance. Hamming distance. This is nothing but, see, each of these point is a group of n bits. Okay. So, if I have, say, for point A, and if I call this point as B, for point B I have these 2 blocks of n bits. Okay. Then there are n bits in each of them. Suppose in representation A, that means point A, in this position there was 1 1, and in the corresponding position there was 1 0 in B, whereas in all other positions they had similar bits. Then we say that the Hamming distance between these 2 code words, I can say, or these 2 points in this signal space is 1. Is that okay? So, because they are different in one place, you can number the places 1, 2, 3, 4 up to n. Now, take 2 points each represented by n bits, and then you can go on comparing position by position and go on counting in how many places they were different. In this example, I said they differ in one place. In A there was a 1, in B there was a 0. So, the 2 points each represented by n bits, they differed at one position, okay, and hence I may say that the Hamming distance between these 2 points is 1. So, as he pointed out, let me say that if the Hamming distance between these 2 points is 1, Hamming distance sometimes is indicated by D capital H. Suppose that Hamming distance between points A and B is 1. Okay, we usually do not associate any unit to that really. Is 1. Then coming back to my question, it does not make much sense really to assign or to encode 2 message patterns to A and B respectively. One message pattern is assigned the point A, the other message pattern is assigned the point B, because then here, as he has already pointed out, if there is one error during transmission, then it may be that, for example, if I consider that this point A, we have mapped a message pattern capital M1 is one message pattern of k bits. After encoding we mapped it to point A, and another message pattern M2, after encoding we mapped it to point B, such that these 2 points had a Hamming distance of 1. Now during transmission there has been an error. What may happen? I mean, it may so happen that the error occurred in this place only. It may so happen the error may occur at other places, any other place really, okay, but it may occur in this position as well really. If the error occurs in this place where these 2 points were differing, then what do I get? If M1 was transmitted, what I get is M2, is it not? And after you get M2, there is no way that you can sense, even you can detect even that there was some error during transmission, because you have already accepted both A and B as valid code words. A corresponded to a message pattern M1, B corresponded to a valid message pattern M2, and hence both A and B are, I mean, you are likely to receive both, I mean, A or B or any other pattern at the receiver. So there may be a case that while point A was transmitted representing M1, you received point B and you are going to decode. You cannot really detect that there was an error really, and you will very honestly would deliver M2 to the information sink. Okay, the purpose is defeated, and hence you have to choose these points. That means you have to map your 2 to the power k points. That means you have to encode appropriately such that the Hamming distance, see the point was between these two adjacent points. While discussing this, I did not discuss about the distance of point A with these further points really. Okay, so you should come up with an encoding strategy such that the minimum Hamming distance, it is not only Hamming distance really, the minimum Hamming distance, okay, between any two code words are nothing but points in this n dimensional space, is as high as possible. Yes, I repeat. Oh, you have a question? Yes.
Sir, if we know that our transmission can, we know that during transmission we can have large, if we are susceptible to large amount of error.
Yes.
So we have to keep the number of n much larger so that as to adjust more. Of
Good guess. Yes. Yes.
so
Yes.
so
If you know that the channel is more noisy, it is likely to cause more errors. He has guessed what has been established by theory also. Shannon has said that yes, it is possible to contain higher number of errors, but in that case asymptotically it will be good to extend, I mean make n larger, that means larger block length you have to choose, then you will be able to still space your points, okay, and maintain a good amount of separation so that you can correct good number of errors. Yes, that's a good guess. Good.
sir, Hamming distance is then defined as the number of bits that are different between two code words.
Number of places in which two code words of same length differ.
So if two code words differ only in MSB and NSB, then Hamming code is 2.
Hamming code is 2. Hamming distance is 2. GH is 2. Any other question? Then let me repeat, a good encoding strategy for block code is to map or to choose the points in n-dimensional code word space such that the minimum Hamming distance is the maximum possible one. Don't get confused. Okay, by minimum Hamming distance we now mean for any code word the minimum distance of the other valid code word. Okay, the distance between two nearest code word is the minimum Hamming distance, and for a good coding style, good coding or encoding strategy, this minimum value should be increased as much as possible. Do you feel there should be some limit in this?
The length of the code limit.
Well, one at a time. Yes.
There should be limit on the length of the code word. We cannot just increase.
Okay. Yes. I mean, as he says, there should be some limit in the value of n as such. Really. Okay. Yes.
The limit is automatically set by bandwidth constraint, because more you have to transmit, faster the rate,
Okay.
higher the bandwidth.
So temporarily I remove this. I'll get back to this after some time. Now, a good encoding strategy then means you place your points as uh, far off as possible, okay, so far as the valid code points are considered. And towards that, one, the limit may be that in many cases you will be given the value of n may be given, okay, and in some cases k also may be either specifically given or some range may be given, so that the rate, code rate will be restricted, and either k or code rate, which is k by n, is given. So, if n is given and then either k or the rate is given, then you can see that the size of the code space is rather dictated really. Then the remaining strategy depends on how nicely you are still able to place your points. You are able to choose the points as valid code word points. Okay. A lot of work has gone into this really, and when I said there are codes called Hamming code, BCH code, etc., a major contribution from them was to devise a coding strategy such that we could select the points ensuring a respectable value of minimum Hamming distance or DH min. Okay. Now, coming back to a bit closer to this issue of minimum Hamming distance. Suppose this value of this situation of dh equal to 1 is not acceptable. We should not ever consider two nearby points, two adjacent points as two valid code words. By valid code word I mean code words which represent an encoded output for a message bit pattern of k really. So, a better situation perhaps would be that if we choose point A as a valid point, I should not choose B, maybe I choose this as point B. Okay. And the nearby points of A like this or this should never be chosen, though those are valid n tuples. So, in a code space, n dimensional code space, we will have 2 to the power n tuples, but all of them are not good or valid code words. We have to select only 2 to the power k code words. Okay. Suppose we have selected A and B, okay, and let me put a few more points. Okay. Now, suppose the code is likely to correct one error, then can you guess what should be the minimum distance or minimum Hamming distance, so that one error can be corrected without any ambiguity? Hmm? One answer is 2, one answer is 3. So, is it that with a Hamming distance of 2 we can unambiguously correct one error always? What I do is that by common sense I draw a line of division, say. Okay, it need not be a straight line really, some boundary, and try to see that if for example there were only these two code words, if the number of code words was 2 only, not 2 to the power k, then I could say that, well, if A was the actual code word which was transmitted, and during transmission because of error, if it was converted to this point, say, which is not a valid code word, say at the receiver, if you try to imagine a little bit, it is not necessary that you get a valid code word always. The error may be of any nature really. So, you may expect when n bits are transmitted, you receive n bits. Okay. So, in general you will receive any of the n tuples, fine. So, I said suppose you have received this n tuple. Now, can you decide by any means that no, the corresponding transmitted code word was not B but A? Three. So, now more number of persons say that 3 has to be the minimum distance. Okay. So, the point is that one can find a decision strategy at the receiver, that is the decoding strategy, okay, by common sense. I am trying to call it as heuristic decoding algorithm. The basic idea is that we have to perhaps identify a region around each valid code word point such that any received n tuple, if it is within the region of that code word, then like say let me now say that this is the region for B, code word B. So, if I get a received n tuple block of n bits which is here, okay, then I will say that no, actual transmitted code word was B, though I had received this. Why did I receive this point? Because of error only. Okay. Then the important issue is how to find this region or domain of B really, so that if I get and receive n tuple within this range, I will just blindly say most probably that corresponding transmitted code word was B. I said most probably. Do you agree to that? Yes. Isn't it? Because error pattern is something which you do not know, you can never bound really. So even if the point you have received here, actually because of many number of errors, this point might have resulted with large number of errors might have appeared here at the receiver end. So we say we find a region such that if I have a received code word within this region, we will say with confidence most probably the transmitted code word was this, and this is justified also intuitively, because we have seen some time back even for the binary symmetric channel where we introduced some epsilon as the transition probability. We observed that the transition probability, which was the conditional probability, usually has a very small value, nowhere near half. The value is 0.01, 0.001, you remember. Okay, what does it mean? It means that if I transmit one bit from the transmitter to the receiver, the probability of error is very small. If say epsilon is 0.001, then 1 out of 1000 bit will be in error. Okay, and if I again assume like we did for the BSC, it was a discrete memoryless channel. Did I mention that? Okay, so if I now transmit n bits one after another, each bit is affected by noise in an independent manner. So, and the probability of error also is very, very small. So, is it not less probable that we have more number of errors over a transmission of n bits? It is more probable that there is no error in a block of n bits. It is to some extent probable that there is one error during transmission of 1 bit. It is less probable that there are 2 errors during a transmission of n bits through the same channel, through the same propagational radio channel. Okay. So, more and more errors are less likely. Okay. So, it is highly improbable that a point, a code word which was this when it was transmitted, because of large number of errors it came into the region of B really, whereas it is highly probable that when I have received this point was actually transmitted and it diverted to this point only. Does it make sense? Okay. So, we have to find a region around each point really. Now we can see by common sense, as he says really, the minimum distance that is necessary for correcting one error is not 2 but 3 really, because there may be a point in the decision boundary, there may be a point really which may be equidistant from both the point, both A and B, and then you are at a loss really. Okay. So, if you have a minimum distance of 3 between any 2 code words, valid code words, that ensures that you can correct a single bit. Okay. In general, if I have to correct t number of errors by extending this logic, okay, we can guess that the minimum Hamming distance should be 2t plus 1. Okay. So, with some gap here, let me write dh min, minimum Hamming distance, okay, should be, let me write greater than equal to, okay, 2t plus 1, where t is number of errors that can be corrected, of course not absolutely, with that possibility that still most likely can be corrected. There will still be a possibility that you some errors will go uncorrected if suddenly large number of errors appear. Number of errors that can be corrected in a code word of length n. Okay, fine. Now, can we summarize the intuitive or heuristic decoding algorithm like this? Then that the encoding strategy we assume to be a nice one, okay, ensuring certain minimum Hamming distance, fine. And then during transmission, small number of errors are more likely, and errorless transmission also is very likely. Okay, higher number of errors are less likely, and hence what we will do is that we are expected to receive any n tuple, need not be a valid code word, and we will just then try to find which is the nearest valid code word in the decoder. In the decoder, we will try to find, after receiving this n tuple and knowing the encoding strategy, the decoder has to know, and then the decoder will try to find out what is the nearest possible code word, valid code word, and once it finds that nearest valid code word, it simply says as if that code word was transmitted, and from that code word it removes that additional parity bits n minus k bits and takes out that message bits, k message bits, and delivers to the subsequent block.
This is a one-to-one mapping.
Yes.
So can we essentially can we practically say that actually say that there are some information bits and some parity bits?
Yes. In fact, these parity bits helped us in putting these 2 to the power k message points in a higher dimensional code word space. Would you repeat your question?
So now we have a k-dimensional space,
Message space,
and an n-dimensional code space.
Yes.
So we have taken out the k point, 2 to the k points, and placed them accordingly, according to a coding strategy, into the n. So do we actually preserve the actual message bits in message symbols in that?
That is this issue we discussed in the last class. Really, the code may be systematic type or non-systematic type. It is, in fact, in this discussion, was it essential anywhere to really find, really ensure that the k message bits should be retained as they are? Okay, it is not necessary for this intuitive understanding. Okay, this helps to some extent in implementation, in hardware implementation. Okay, and also in understanding in the theory to some extent. It is not absolutely necessary really, because what is important is the encoding. The point he has a point once again is that whatever is the encoding strategy, okay, the encoding strategy has to be intelligent. It must be mapped. Okay, and some kind of reverse strategy also should be possible. That means, if in the process of encoding in a non-systematic manner, we have mixed our information bits in a code word, in the decoder, after the decision have been taken really, I should be able to get back my original k message bits from that mixed up group of n bits. That has to be there. Otherwise, I appreciate his problem now. Otherwise, how do I get back my k message bits? So, any encoding strategy should be clearly defined such that from the code word, if there is no error, from the code word, we should get back the corresponding message portion. Okay, for that, let me then, this is the end of my intuitive discussion of the decoding algorithm. Is that okay? If you have any question, ask me. If not, then let us go a little bit into how it is done, and I'll just try to give some general indication which will be applicable to many of the block codes. Okay. In the next class, we'll discuss briefly about the theory of, a little bit of theory about, or general strategy about encoding, okay, and ultimately end up with Hamming codes.